This is the first lesson in our completing the model of the atom unit. In this lesson, we will be looking at learning goal 1A for the unit, the wave model of light. Our success criteria for this learning goal, you can see on this slide. This learning goal is I understand the wave model of light. In this particular video, we will look at these three success criteria. The first of which, I can explain the relationship between the speed and wavelength and frequency of an electromagnetic wave. So in these first couple slides, we'll just look at some basic properties of waves, and we'll examine this term electromagnetic wave. So light is a term we are all familiar with. That is just the more common name for any electromagnetic wave. Obviously, the word light is much easier to say, less syllables. The term electromagnetic wave sounds really confusing, and in some ways it kind of is. It's kind of complex, but we just refer to that as light. So what an electromagnetic wave is, or what a light wave is, and the reason why it's called an electromagnetic wave, is it's an oscillating electric and magnetic field. So if we were to have some sort of schematic or model of what an electromagnetic wave would look like, what you'll notice here is it's really two different waves, an electric field wave, which we see here in red, and a magnetic field wave, which we see here in blue, that oscillate together, that oscillate in sync. When we say in sync, what I mean by that is notice here on anytime one wave is at a node or a 0 point, so is the other. Likewise, when one wave is at a maximum, or what we call a crest, so is the other. So that's what we mean when we say they oscillate in sync, or they oscillate together. And then this arrow here that runs through the middle is just indicating the direction of propagation. In other words, which way the wave is moving through space here. Now you'll notice on your note sheet there that there's a place for you to draw this. Now if this were me, I would have a really hard time drawing it because I'm a terrible artist, and trying to draw these three-dimensional looking shapes on a two-dimensional piece of paper is kind of hard. So I would just encourage you to sketch something out that makes sense to you, to help you understand what we mean by this electromagnetic wave with this oscillating electric and magnetic fields. All right, going to our next slide here. So properties of waves. So whether we're talking about a light wave, meaning an electromagnetic wave, or a sound wave, or an ocean wave, all these waves have similar properties. One property of a wave is known as the wavelength, and that's just the distance between any two equivalent points on a wave. So for example, if we had these two waves here, so these are two different waves, and now these aren't pictures specifically of light waves or electromagnetic waves, these are just waves in general. Notice to measure the wavelength, we can measure from one crest or peak to the next peak or the next crest. And notice this wave here on top has a shorter wavelength than the wave here on bottom. Now we wouldn't have to measure from crest to crest. We could measure, say, from trough to trough, or the bottom to bottom. We could also measure from one equilibrium point, equilibrium is when it's right in the middle, to the next matching equilibrium point. Now when we say matching, it wouldn't be, say, from this point just to this point. Well, actually, let me go down here on the longer wavelength one. It'll be easier to show you with my pointer here. The matching point would not be, say, from this point here to this point. It would be from this point to this point over here. The reason being is, for example, crest to crest, notice we've gone through one complete cycle of the wave. Whereas if we're measuring from equilibrium points, if I go from here to here, that is not a complete cycle. I would need to go from here, just following the wave, it'd go down, it'd go all the way up, and then back to where it started. That would be a complete cycle. So notice here we have a shorter wavelength in this picture than we do here. So that's one property of a wave. Another is known as frequency. And the frequency of a wave is just the number of waves that pass a given point per second. Now this is related to the wavelength, as we'll see here. Here again, I have two different waves here, one with a short wavelength, one with a long wavelength. Notice the shorter wavelength would have a higher frequency. Because just imagine if you were just standing here along the side of these two waves here, and these waves were passing you, assuming that they're going the same speed, This particular wave would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different wavelengths that would pass you, whereas this would only have 1, 2. And so if both of these went by you in, say, 1 second, this here would have a frequency of 12 oscillations, or 12 waves per second. This one would be 2 waves per second, or 2 oscillations per second. So we can see here that as the wavelength gets shorter, the frequency goes up. Likewise, the longer the wavelength, the lower the frequency. Now these two are related by the speed of the wave. That's just how fast the wave moves through space. Mathematically, they're related by this equation here, that the speed of any wave equals its wavelength times its frequency. Another way of saying this is that wavelength and frequency are inversely proportional. Now, to a lot of people, they see that and they would think that that means, well, if one goes up, the other goes down. And that is partially true. Well, that statement is true, but it's incomplete. It's not just, say, if the wavelength increases, the frequency decreases. It is much more specific than that. Say, for example, if we were to triple the wavelength, if the wavelength were to get 3 times greater, the frequency would have to be divided by 3, or be 3 times less. Because no matter what, they always have to multiply to equal the speed. And if the speed's the same, then whatever factor of change one of these has, the other one has to have the inverse of that. So again, inversely proportional would mean, for example, if we were to divide the wavelength by 4, be 1/4 of what it was, the frequency would have to be 4 times greater than before. That's what we mean by inversely proportional. All right, please pause the video and complete that check for understanding question set number 1. All right, you've had a chance to do that check for understanding number 1. We've looked at this first success criteria. Now we're going to go to success criteria B here. We're going to calculate the wavelength and frequency of an electromagnetic wave. So we're going to apply that equation that we just looked at from the last slide. Now, more specifically, when we talk about calculations for electromagnetic waves, there are some symbols that are commonly used with this. One thing we want to recognize is that the speed of any electromagnetic wave is just the speed of light. You learn about light in other classes, and I'm sure you've heard this phrase before, speed of light. When we say the speed of an electromagnetic wave, that is the speed of light. So that equation from the previous slide, we can actually write now, not just speed, but specifically the speed of light equals the wavelength of the wave times its frequency. Now the symbols that get used for those quantities are as follows. The common symbol for the speed of light is the lowercase letter c. The symbol that gets used for wavelength is this Greek letter. This is the lowercase Greek letter lambda. When you write it by hand, it just kind of looks like you're making an upside down letter Y, you can see there. So that is the symbol that is commonly used for wavelength. And then for frequency, the common symbol that's used with this is the Greek letter, lowercase letter nu. It kind of looks like just our lowercase letter v. Depending on what font you have your typeset in, if you're typing, it can look a little more curved or a little more wavy. If you just want to write a normal V, that's fine. There's nothing wrong with that. But what you want to do is you want to remember, you need to memorize what these symbols are here. Okay, I will always give you this equation. You don't need to memorize the equation, but you do need to know what the symbols mean. And so notice there's a place on your note sheet there to write this equation and to indicate what each of these symbols are. So you need to know what C stands for, what lambda stands for, what nu stands for. All right, the speed of light in a vacuum. And now vacuum just means an area of space where there's nothing. We're not talking about what you clean your carpets with at home. The speed of light in a vacuum is a constant, and it is, you can see it here, it's almost 300 million meters per second. 299,792,458 meters per second. Now you do not need to memorize that number, nor do we ever use that number exactly because we don't really ever need that many significant figures. The number we will use is this. We'll just say it's 300 million meters per second, and to 3 sig figs it is. So C equals 3.00 times 10 to the 8th meters per second. Again, you will not need to memorize this. I will give you this constant value on any assessment that you take. That being said, you guys are going to have it memorized here in a couple of days because you'll use it so often. But this is the value that we will use for the speed of light to 3 sig figs. If we would ever need more than that, then we could look it up, or we could just go back and use this value. Notice that there would actually have 9 significant figures. Let's talk about some common units for these other two quantities, wavelength and frequency. So a wavelength is just a length. So the base unit in the SI system would be the meter. So that's commonly used, but so is a nanometer. Oh, I just realized I spelled that wrong. That should be N-A-N-O, not nano. The nanometer, which is 1/1000th of a meter. And the reason why nanometers is commonly used is because for visible light, what we can see, that has a range between roughly 400 and 700 nanometers, so it's pretty convenient to use. And one thing you'll want to recall then is just our understanding of the SI prefixes. Nano is 1/1000th, so there would be 1,000,000,000 10 to the 9th nanometers in 1 meter. That's a conversion that we will use quite commonly whenever we're doing these sorts of calculations. So that's a common unit for wavelength, meters or nanometers. For frequency, the common unit of frequency is known as the hertz, and that symbol is the capital H, lowercase letter Z. And at first it might seem like, geez, how is that the unit for a frequency? Well, 1 hertz is the same thing as 1 wave per second, or 1 inverse second as it's sometimes written. So you might see it like this, seconds to the -1 power, but that's the same thing as just writing 1 over seconds. So our frequencies are given in hertz, which is, again, is 1 oscillation or 1 wave per second, but commonly written just as 1 over seconds or just as hertz. And so we'll see in these example calculations coming up what that looks like. All right, so example number 1. So you'll notice on your note sheet that this question is already written out there. So as we go through the example, you can just fill in the notes here of how it's worked. You don't need to worry about writing the question. So example number 1, microwaves are used to cook food and transmit information. What is the wavelength of a microwave that has a frequency of 3.44 times 10 to the 9th hertz? So notice the term microwave, yes, that's what we call that box that you have in your kitchen, but the reason it's called that is because that microwave oven produces or emits microwaves, which is just an electromagnetic wave, and that frequency is lined up with the frequency that the water in your food vibrates at, and that's why it heats up. Anyway, so this question here is asking us to find the wavelength, and we're given the frequency. So we want to start with that equation for the relationship between wavelength and frequency. Just going from our last slide, remember that C equals lambda nu. Again, you won't need to memorize the equation. I will always give it to you, but you do need to know what all the symbols are. So we need to know that C is the speed of light, lambda is the wavelength, nu is the frequency. So on this problem, we're asked to find the wavelength, so we need to solve it for the wavelength. The students that do this most successfully, they do not try to go straight to plugging numbers in a calculator. They do not even start by writing numbers down on their sheet. They use equations. So you'd write this equation here first. Now you're going to solve it for wavelength. So solving it for wavelength, remember lambda, that upside down y is wavelength. So to solve it for lambda, I need to divide both sides by nu. Okay, nu is that V looking symbol. So if I divide both sides by nu, that will give me lambda equals C divided by nu. Now that we have an equation for the wavelength, now we'll substitute in our numbers. So substituting in our numbers, so recall C is the speed of light, and again, you do not need to memorize this value. I will give it to you. C is the 300 million, or 3.00 times 10 to the 8th meters per second, and we're given the frequency. That's 3.44 times 10 to the 9th hertz. So now that we've plugged our numbers in, it's just a matter of getting an answer via our calculator and making sure our units are right. Speaking of the calculator, you may need to go back and review and practice how to use the scientific notation on your calculator. Remember, you don't want to hit the times button and then hit 10 and then hit the caret. use that enter exponent button on your calculator. This makes this much easier. So if you plug all that into your calculator, you should get this value, 0.0872. Notice both of these measured values have 3 sig figs, so our answer can't have any more than that, so they're 3 sig figs. And our units here are in fact meters. Now one of the things I would highly encourage you to get in the habit of doing is to do a unit check, where all I'm going to do here, I'm going to forget about the numbers, I'm just going to write out the units of my calculation here. So notice I have meters per second divided by hertz. Now at first it looks like that's not going to really work out very well, but remember that unit hertz can be written as inverse seconds or 1 over seconds. And when I do that, you'll notice the seconds in the meters per second will cancel with the seconds from the hertz, because the seconds in the meters per second is in the denominator. The second for the inverse seconds is in the denominator of the denominator, which actually means it's in the numerator. So they cancel, and we're left with meters, which makes sense because we're finding a wavelength, just the distance between 2 equivalent points on a wave. So that makes sense, so that one checks out. So our answer there is the 0.0872 meters. All right, going to the next example problem. And again, notice on your note sheet, this is already written there, so you just need to follow along and jot down the solution. So example 2. Light reflected from a green leaf has a wavelength of 490 nanometers. What is the frequency of the light? One thing I'll point out here, actually a couple things. Do notice this decimal point after the 0. That's notation we don't see too often. What that's telling you there is that 0 is significant. If I did not have that decimal point there, then that 0 would not be significant, and that would just be 2 sig figs. But because that decimal point is there, then the 0 is significant, and that's 3 sig figs. The other thing I'll point out here, and you'll see once we start plugging the numbers in, really be careful with your units. Because we're given this this wavelength here in nanometers, we're going to need to make sure we get the unit canceled properly. So again, like before, this question is asking us about the relationship between wavelength and frequency. So I'm going to use that same equation, C equals lambda nu, but this time we're asked to find the frequency. So I want to solve it for the frequency. So I want to divide both sides by lambda. That will get the nu by itself, so I get nu equals C divided by lambda. Now we can substitute in numbers. So notice when I do that, and I've actually kind of already done a second step on here, just ignore this conversion factor for now, this 10 to the 9th nanometers per meter. If you just look at this left side here, my numbers, my speed of light, 3.00 times 10 to the 8th meters per second, is my speed of light divided by my wavelength of 490 nanometers. Notice meters and nanometers don't cancel. Okay, they are not the same unit. So you can't look at this and say, oh, there's meters and there's a meters there, so they're going to cancel. Because remember, nano itself is not a unit. Okay, nano is just a prefix. That whole unit there is nanometers. So we have to cancel the nanometers in order to get to meters, and then those meters will cancel. So this is why we really need to remember that conversion factor. There are 10 to the 9th nanometers, and notice I put that on the numerator here on top to cancel with this nanometers, for every 1 meter. And notice now this meters here in the denominator of the conversion factor will cancel with this meters there in the meters per second. And so if you plug all that into your calculator, you will get 6.12 times 10 to the 14th will be the number. Again, don't forget, practice that scientific notation. And the unit here is hertz. Now, again, you might be wondering, how in the heck do we get hertz? I don't see hertz here anywhere. Well, this is why you want to make sure you check your units. So I'm just going to write out the units of the calculation. And again, thinking about what cancels, my nanometers cancels, because one's in the numerator, one's in the denominator. My meters cancel, because one's in the numerator, one's in the denominator. And you might be thinking, well, that should just give me seconds. And I see students every year will tell me that this unit here, the frequency equals some number of seconds. Well, I want you to think about that. The unit seconds is not a unit for frequency. If you are giving the unit of seconds, that would be a time. So that should set off some alarm bells in your head right there. If you are listing the answer to this calculation with the unit seconds, you know that can't be right because we're not finding a time. So the key here, recognize this seconds is in the denominator because it's meters per second. So it's 1 over seconds. So that is what we call the hertz. Now, if you wanted to, you could list the answer here as 1/seconds. You could list it just like you see written here. But more commonly, it is written as the unit hertz. All right. So you've seen a couple of examples. So go ahead and pause the video. There is another calculation there for you to practice. That's the check for understanding question number 2. All right, so we have looked at how we calculate the wavelength and frequency of an electromagnetic wave. The last success criteria we'll look at from this lesson, and this will not take us long, is how do we order electromagnetic waves by wavelength and frequency. So the electromagnetic spectrum, as you guys saw in that short video we watched in class, that the visible light is only a really, really tiny fraction of the electromagnetic spectrum. So here is a schematic of the entire electromagnetic spectrum. Now, one thing I will point out here is this is not drawn to scale, but notice at one end of the spectrum, these really short wavelengths. So notice the picture here. We have this wave here. We're representing really short wavelengths here. Would be gamma rays. Okay, that's an incredibly short wavelength. I know it's kind of small. That is 10 to the negative 12th meters. Now, you don't need to memorize these numbers here. I'll tell you what you really need to know here from this picture here in just a second. But 10 to the negative 12th meters, that would be a picometer. That's a trillionth of a meter. So incredibly tiny, tiny, tiny wavelengths, these gamma rays. And then as they get a little longer, we call them X-rays. And yes, those are the same things we talk about when you go get your go to the dentist to get your teeth X-rayed, or you have a broken bone. That's what the X-ray is. It's just a wavelength of light that's shorter than visible light. Then we have ultraviolet. Then we have visible. Then we have infrared. Then we have microwave. Then we have radio waves. So one of the things that will be important for you to know here, and you will need to memorize this, is you'll want to memorize this sequence here, this order. And you need to know which end is the short wavelength. So the gamma ray end is the short wavelength. The radio wave end is the long wavelength. Now within that, we also need to recognize the order of the visible light, the colors. So notice this picture here, and again, this is not to scale because the visible light spectrum makes up an incredibly tiny, tiny fraction of the electromagnetic spectrum. But if we were to spread it out and take a look at it, this is what we have in our visible light spectrum. And we want to know the order of the colors as well. The easiest way to remember those is to remember the made-up name that is Roy G. Biv. And actually I have that on here, and I put them all in the corresponding color. So the order is red, orange, yellow, green, blue, indigo, violet. Okay, so if you remember that, Roy G. Biv, that will give you the order of the colors, and notice how it fits into this spectrum. So in between infrared and ultraviolet, okay, notice the red end would be closest to the infrared. The violet end would be closest to the ultraviolet. That's the order of the color, that the colors go. I am convinced that the color indigo, that name, was invented just so we could have a letter to put in here to make this a nice handy dandy name to remember. So indigo, in case you're not familiar, is kind of a bluish purple, and you can see that there. Okay, you'll see on the note sheet there aren't any examples here, but I think this picture is pretty self-explanatory. On the note sheet, there's a couple of questions here that have you use this graphic, this image, to order these waves by frequency and wavelength. So just remember, gamma rays, it starts at the short wavelength, radio waves at the long wavelength. In terms of frequency, remember from the first success criteria, it's just backwards from that. So short wavelength would mean low frequency, long wavelength would mean high frequency. And so you can use this graphic. I would pause it, take a couple minutes, try to memorize it. You won't get it all memorized in a day probably, but give it a shot, and then over the next few days you just keep practicing memorizing this order. And don't forget, include the colors in your memorization as well. All right, this concludes the video for this learning goal on completing the model of the atom for learning goal 1A, and we will pick up with the next learning goal on the next video.